of creating isotropy, of making our quadratic form isotropic. And because of that, the first isotropy index is also the minimal positive isotropy index your quadratic form acquires over an arbitrary, over a field extension of the base field. So it's also the way of thinking of it. And also, if the quadratic form is not totally isotropic, I will define it later, totally isotropic. So if it is not, and this is our main case of interest here, then instead of isotropy index, you can use the Witt index as here, and you will get the same integer. So the first isotropy index can also be defined through this formula with isotropy index replaced by Witt index, if the quadratic form is not totally isotropic. And again, the integer you get will be the minimal Witt index. The quadratic form requires positive Witt index. The quadratic form requires over an extension of the base field. Okay, so this is a meaningful, important invariant of the quadratic form, and the conjecture from the title, which is actually a theorem now, but I will still refer to it as the conjecture, says that, so it's about the possible values of this first Witt index, and the statement is as follows. First Witt index of phi is less or equal to power 2 to the n for maximal 2 power dividing the difference between dimension and the first Witt index of phi. So I think it's the shortest way to formulate this conjecture, this condition. But you should really think of it as, so we just fix some, let's fix some dimension of quadratic forms we're interested in, and then look at all values of the first Witt index which satisfy this condition. So you will get a list of some allowed values and list of some forbidden values. And maybe let me say right away, so that all forbidden, so all non-forbidden values are really possible. So this is a sort of best statement you can do. And so all non-forbidden values of I1 of phi are possible. There are examples for this. I won't discuss those examples. So let me give some examples for some special dimensions of quadratic form. So for instance, if dimension of phi is 2 power, I will use the same n, well, it's just some power of 2 plus 1, then the only value allowed by this conjecture is 1, the value 1. So this is very restrictive in this situation. So let's now look at the case where dimension is 2 to the n plus 2 to the m plus 1, with n strictly bigger than m, strictly bigger than 0. Then there are two values which are allowed. So one of them is 2 to the m plus 1, and the other one is 1. And more generally, if dimension of phi is odd and you write it as a sum of 2 powers, then you basically get all possible values for the first Witt index, taking partial sums. So the number of possible values is the number of 2 powers greater than 1, so something like that. So 2 here, 1 there, and in general, still much less than what you would expect probably in the beginning if you never seen this invariant before. So this conjecture really eliminates a lot of values which could be a priori possible. And so as to the authorship, so the statement, so the conjecture has been formulated by Detlev Hoffmann. So he did it in 4 fields of characteristic different from 2. Because it was in 98 and people didn't care much about characteristic 2 for quadratic forms at that time, I think. But then Burt Totaro extended this statement to arbitrary characteristic. And so he did it in the paper where he treated quadratic forms in characteristic 2 and proved another important result about first width index of quadratic forms. So this was published as preprint in 2006, but then the paper appeared in 2008. Okay, so this was the statement. Now, what about contributions to the proof? So maybe the first one I mentioned is the Hoffmann separation theorem, the famous one. Which again is a statement on related matter. And as a consequence from this theorem, which was proved in 95, so again for characteristic not 2, so everything from the previous century was for characteristic not 2. And as a consequence from this theorem, you get, for instance, example 1 here already. And more generally, you get the inequality I1 of phi is less or equal than m if you write dimension of phi for dimension of phi equal to 2 to the n plus m with m between 1 and 2 to the n. So just write dimension of phi in this form. Then from this conjecture, from the statement of this conjecture, you get this inequality. And this inequality was known since the proof of Hoffmann's separation theorem. In characteristic not 2, in characteristic 2, this has been done by Hoffmann and Legrebi. So we may call it Hoffmann-Legrebi separation theorem if we mean arbitrary characteristic, and this was done in 2006. The characteristic 2 edition. Okay, then other contributions, for instance, by Oleg Ishboldin. This was one of his last results, proved in 2000. So he proved that first width index of phi is not m-1. So again, for the same situation, for the same m related to dimension of phi, first width index is not m-1 if m is not 2. So again, this is something that you can deduce from the statement of the conjecture, and this was proved in 2000, so still in characteristic not 2 here. So another set of cases was done by Alexander Vyshik, same year. So he just proved the conjecture, checked the conjecture for all forms up to dimension 22. So complete proof up to dimension of phi being 22, and actually Detlev did it up to dimension 10 in 98 already. Okay, and then I published complete proof in 2003, so still in characteristic different from 2. So complete proof of the conjecture, but still for characteristic different from 2. And I use input from other people. So 2 main things were so Wyszyk's results and methods of investigation quadratic forms through consideration of considering motifs of quadratics, so things related to this. And the other, so probably most sophisticated contribution was the Steinert operations that appeared not a long time before this date. So Steinert operations. So what was needed here were Steinert operations on Chow groups modulo 2. And so this was initially done by Voevodsky in the larger context of motivic cohomology. And then made by Patrick Brosnan, much more accessible in this particular situation where we are only interested in Chow groups and not in the entire motivic cohomology. Okay, so this was done before. So basically only characteristic 2 case remained in this conjecture. And in characteristic 2, there are basically two difficulties or differences within characteristic not 2 case. So first of all, there were no Steinert operations like the one I'm talking about here. So on Chow groups modulo 2 in characteristic 2, no Steinert operations. And this was sort of main difficulty here. But now we do have them, so there is no anymore. And so we have Steinert operations constructed by Eric Primozic. And this is only last year, 2019. And so having enhanced the Steinert operation, we can do a non-singular case in a very similar way to the characteristic different from 2 situation. So this was done by Eric Primozic as well. So non-singular case, non-singular or non-degenerate. So the case of a non-degenerate quadratic form was done, but this was not everything, because this is another specific thing we have in characteristic 2. So in characteristic 2, an isotropic quadratic form we are talking about in this conjecture can be degenerate. Is not necessarily non-degenerate, can be degenerate. And this precisely means that the corresponding quadric X can be singular, can be non-smooth. Yeah, and so this is the main thing the main issue I'm going to discuss in this talk. Before I go to details here, I want to add that Concerning the first difficulty, there were also partial contribution by Olivier Authion. He constructed some standard operations in characteristic 2, not all of them, and also some replacements, some weaker replacements for standard operations. And using this, he were able to get some results before Eric did it in last year. He was able to prove some partial results towards this conjecture of the kind that, for instance, if we know that difference between dimension of the form and the first width index is not divisible by 4, then he was able to prove that the first width index is at most 2. So such a thing. And for this, you only need first and second standard operation, and he constructed such. So this is the history. And so now let me go to discussion of degenerate quadratic forms in characteristic 2. So, to talk about this, it's very useful to consider the totally singular part of our quadratic form. So we start with our phi. In a moment, I will have to assume that phi is not 0. Clearly, it's okay, this assumption. So let's define phi prime as the restriction of phi. We just take the map phi and restrict it to the radical of the bilinear quadratic form associated to phi. So standard notation is b phi. For this bilinear form, it has a radical, and we restrict phi to this radical, and this is phi prime. So it's a subform of phi, and it is called the totally single part of phi. Other people also call it a quasi-linear part of phi. And we get the corresponding projective quadric x prime sitting inside of x as a closed subvariety. So x prime here is the quadric given by phi prime. And basically this is non-smooth locus of x. So x prime is a non-smooth locus. Whatever it means. Well, actually, more precisely, so if you look at the difference, this is the open piece of x, and all points here are smooth, so it's a smooth variety. And actually, all points on x prime are not smooth, so there are no, x prime is nowhere smooth. Well, at least what I certainly can claim is that x is smooth if and only if x prime is empty set. Okay, so smooth quadrics are quadrics where the quadric given by the totally singular part is just empty. Okay, and so once we have this, it's certainly interesting to look at the extreme opposite to the smooth case, which is the so-called totally singular case. This is the case where x prime is just the entire x. Or in other words, phi prime is the same as phi, so radical of phi is the entire vector space. And well, this case has been done also earlier by Stephen Scully. in 2016. And it was done by completely different method compared to what I'm going to present here. So much less geometric, much more algebraic. And so I'm not going to consider this case at all. So I'm basically, my intent is to explain how the proof goes in the non-smooth, non-totally singular case. But before I can do it, I have to recall how the proof goes in the smooth case. So otherwise, I can do. So let me briefly recall the proof for smooth X. So the proof goes as follows. So we start with some forbidden value of the first fit index. We assume that for some given quadratic form phi, non-degenerate one, we get a forbidden value, forbidden by the conjecture value of the first fit index. Well, then we get totally isotropic subspace of this forbidden dimension. All right, so W will be total isotropic subspace where, well, not in V itself, but in V over the function field of the quadratic. Totally isotropic subspace of such dimension. Okay, then this W gives us a projective space sitting as a closed subvariety inside of X over its own function field. And well, this X over its own function field, at least as I said, sits inside of the product of X with itself. So if I think of this X as one copy here, and the function field of X as the function, the residual field of the generic point of X, then I have this inclusion, and I can take the closure of this projective space inside of X squared. And this way I get a cycle, an element of the Chow group, alpha. So it will be an element of the Chow group modulo 2. This is my notation for the Chow group modulo 2 of X squared. So Chow is usual Chow modulo 2. So we get this special cycle on X squared, and we start playing with it. So the problem for now is that we can't say much about this Chow group of X squared. So we want to go to something which we understand better. And so for this, we choose the same Chow group of the same variety, but considered over an algebraic closure of the base field. So let alpha bar is the image of alpha in the Chow group X bar squared. So X bar is X over algebraic closure. Okay, so we get an element here. And we know that, well, by the very definition, by the very construction, this element comes from the base field. So we call such elements rational. Oh, maybe not the best terminology for this, but it became standard already. So we get a rational element in the Chow group of X squared over the algebraic closure. And now we use operations, several types of operations we have.
Karpenko qui cause, qui la connaît, qui en a 10 000 autres jours.
Someone's microphone is not mute. Operations.
Is there any question or someone?
Okay, so operations on, we actually look at all possible powers of x, not only on the square. So chow of x bar r for arbitrary r. So it's sort of bi-graded object. So the chow group itself is graded. And then we also have different powers of x here. And we look at several types of operations preserving rationality of cycles. Preserving rationality. Well, these are roughly pullbacks. Push forwards. With respect to partial projections and partial diagonals. So between different powers of x you have here. Then we also have products or external products. And now the last important thing are standard operations. By which I mean the standard operations of cohomological type. And if I look at the total standard operation, S, it's just a map from chow for every R. I can go from chow x bar R to itself. And this is a non-homogeneous ring homomorphism. Ring homomorphism, non-homogeneous one, which commutes with pullbacks, so respecting pullbacks, and which, with respect to push forwards, satisfy the Riemann-Roch type formula. Yeah, and well, I mean, this is the operations we have, and then we start applying this operation to our special element. Okay, well, what we also do, we use sort of trivial elements coming from the projective space where x is sitting. So embedding of x into the projective space of V gives us map from chow of the projective space to chow x. And so this way we get a lot of elements here, which are not interesting because they come from projective space, but still useful in this business. And so applying all these operations and using all these elements, what we get in the end, we get the class of rational point in chow 0 of x bar. And so this way we see that the class of rational point here is rational, because our operations respected rationality. We started with a rational element, and elements we get here are also all rational when we go to chow x bar, right? And so once we know that the class of the rational point is rational, then we conclude by Springer theorem that X is isotropic. And this is a contradiction. Well, because in our conjecture, we are dealing with anisotropic quadrics. So this is how the proof works. And so you see that, you don't need X to be smooth for everything here, but for certain things you do need it. So first of all, when we look at pullbacks for diagonals, for instance, right? You need the variety to be smooth. For projections, it's fine because they are flat, and so there is no problem with pullback. Well, for products, well, if you don't speak about external products, but usual products, again, you need variety to be smooth. And for standard operation, well, since I said it's of homological type, so you need the variety to be smooth. And also, since I'm referring to the paper by Primozic, where standard operation were even of homological type were only constructed for smooth varieties. So again, we need the variety to be smooth. So we can't immediately apply all these to the non-smooth case, and we need some modifications. So now I come to the core of the talk. I'm starting to consider a non-smooth variety X. Okay, so we have our X prime, which is the non-smooth locus, and we can consider the difference. Let me call it U. And since I want to be away from the totally singular case, my U is non-empty. Well, here is the sort of main observation. So I am interested, as before, in this image, chow of X to the R, arbitrary power, going to chow X bar to the R. And it turns out that this change of field homomorphism factors through the chow of UR. So here we have surjection, just restriction to open piece. UR is an open piece of XR. And it turns out that there is a map here. Okay, so this is already something. Well, for this to work, we need X prime to be anisotropic. So for X prime anisotropic. Well, since basically we start with anisotropic X, X prime is automatically anisotropic in the beginning. And so this will work. And this makes us believe that on the image we have here, on the image of this or image of that, doesn't matter, we will still have all our operations here, right? So the ones which need to exist, X to be complete, well, are there anyway. And since now this image also is the image of chow of a smooth variety, it seems that we will get also the operations that we get because the variety is smooth. Well, actually what we need to have it is that the kernel here is an ideal, stable under, well, it should be stable under standard operation and diagonals. and pullbacks for diagonals. So let me write just delta star. And so why is it like that? Well, the point is that we can actually draw slightly larger diagram. So let me do the same first. So now I go to Chow UR. I shouldn't go to Chow U bar R. This will be something really small, and my X prime won't be anisotropic anymore. But I can go to Chow of UR over the separable closure of the field. So here I'm talking about algebraic closure of the base field. And here I consider U over the separable closure. And the point is that totally singular, anisotropic totally singular forms remain anisotropic if I make a separable extension. So X prime sep is still anisotropic. And because of that, I have diagram like here. And everything is fine with this arrow. It's just change of field homomorphism, which is respected by the Steinert operation and everything, and multiplication. But what can I say about this arrow now is that the kernel here coincides with the set of numerically trivial elements. So here I need to explain something. So first of all, what are numerically trivial elements? Usually you define numerical equivalence for smooth complete variety. So if Y is smooth complete, then you say that alpha in Chow, well, I'm still working because I only needed Chow group like that, Chow group modulo 2. You can work with any coefficients in this definition. So alpha is numerically trivial if degree of alpha beta is 0 for any beta in Chow Y. So you just take an arbitrary cycle on Y, take the product, which you can take because Y is smooth, and then you look at the degree map, which you have because Y is complete, and degree map is the push forward for the structure morphism of Y. So it's a homomorphism from Chow Y to the coefficient ring, which is F2, the field of two elements here in our situation. Well, this actually goes to Chow 0. If you apply degree homomorphism to a cycle of positive dimension, you just get 0. But it's more convenient to think of it this way. And then this is a numerical equivalence. So how can I consider a numerical equivalence for my variety U, which is non-complete? Well, it is smooth, so there is no problem with smoothness, but it's not non-complete. So the thing is that we can write down the exact localization sequence for X prime, X, and U. Okay, and so, let me do it just for U, not for power of U. So X prime is anisotropic. So here I have my degree maps. which form commutative diagram. But X prime is anisotropic, and therefore degree map here is 0. And therefore I get degree map on U. So we get a degree map for U, and therefore we can consider numerical equivalence defined just the same way as here for a complete variety Y. So I think it's a situation which occurred already several times in that we get, so we get and successfully apply a degree map for non-complete varieties. But for this very situation, it has been considered in Totaro's paper as well. So I just do the same thing as there. But then I consider numerical equivalence, and it turns out that the kernel here I'm interested in coincides with the set of numerical trivial elements. And then it's a standard argument to show that everything is fine, that this is an ideal. The set of numerical trivial elements is an ideal, and this ideal is stable under the Steinert operation. Again, this is something very standard. Well, maybe for Steinert operations it's not that standard, because Steinert operations is not so classical thing. So stability, let me say about this stability under S. So what you want to show is, given numerically trivial element, you apply some component of the total Steinert operation, say Sn. And so you want to show that this is also numerically equivalent to 0. So for n equals 0, so we can do it using induction on n. For n equals 0, as 0 is identity, and so everything is fine. And for positive n, so what you basically need is to verify the formula that the degree of Sn of alpha multiplied by any beta is 0. And you do it using the formula, the Riemann-Roch formula for degree map, which looks like, so degree of Chern class, total Chern class of minus tangent bundle. So let me put Y here. So this could be arbitrary variety Y. And then I write the total Steinert operation of the product alpha beta. And you may assume that alpha beta is of positive dimension, because n is positive here. And then the Riemann-Roch formula will tell you that this degree is 0. So now just look at individual component of what you have here, then you will see Sn of alpha times beta there, the term you are interested in, and all other terms will have a smaller Steinert operation with smaller number, and then by induction assumption, the corresponding degree will be trivial, and then you are done. So this is roughly how you show that the set of numerically trivial elements is stable under the Steinert operations in the case of smooth complete variety. And as I said, in our situation of U or U or a power of U variety, which is smooth but not complete, since it behaves like a complete variety in the sense of existing of degree map, So all arguments go through, and we are done. So I think I'm close to the end. I probably say the last thing. So, I mean, previously in the smooth case, we were working inside of this degraded object, right? And so we used all operations. And the probably should go a little bit further here. So the advantage of this object was that everything was very easy to compute here. And for instance, if we are talking about R's power of our quadratic, then the chow group we get is just 10 to the power of chow of x bar. Okay, and what is the replacement of this simple object where we can everything calculate in our situation now, where the variety x is not smooth anymore? Well, our goal is this image chow well, you are in chow x bar r. Well, this is still something mysterious. We probably can't describe it explicitly, but this is inside of the image where we start with the separable closure. And if we simply stay here, then we still have something mysterious, which we are not able to compute entirely. But when we look at this image, then we get something simple. So first of all, it's the same as chow image, which we get when we start from x sep r. And the chow group, let me again talk about just one copy of x sep. Chow group of x sep is sum of three summons. So two of them are just chow groups of projective space, well, of some dimension. Let me use n again here. Well, I actually want to write down some graded formula. Then I have some shift of grading here. And in the middle, I have some mysterious summand, namely chow of x prime sep. So x prime is our totally singular part of our quadratic. And even when we look at it over the separable closure, I don't think we can understand it completely. So formula is like that. So here, the n which appears here is the number of hyperbolic planes we can extract from our quadratic form phi over the separable closure. And then what remains is simply f prime sep. Okay. So here we have some mysterious part, but the point is that this part completely disappears when we go to the algebraic closure. So this one vanishes over f bar. And then we are left only with these two summands, which we understand entirely. And so we get some very simple explicit object on which we have some operations due to our previous discussion. So exactly the same type of operations which we had in the smooth situation. And so now I can finish by saying that, so everything, so the method we applied in the smooth situation works in this non-smooth situation as well, because we really obtained an object very similar to the smooth case. Okay, so I guess that's all I wanted to say, and I think that I almost used 1 hour for this. Thank you for your attention.